Welcome to Brain Vision.
Hi, the arrangement of an insulated wire is shown in the figure. This is the wire which is bent in a U shape. The ends of this wire are dipped into the mercury like this. Both the ends are dipped into the mercury up to the same depth. And this depth of the wire which is dipped into the mercury has been given as 2.5 centimeter. Here also, this is 2.5 centimeter. Then there is a circuit completing this mercury bridge with the wire along with the cell, having a potential of 1.50 volt. The length of this straight segment of the wire is given as 15.0 centimeter. So we can write it here. This is L is equal to 15.0 centimeter, or we can say this is 0.15 meter. Mass of this wire is given as 5.40 into 10 raised power minus 5 kilogram. And the length which is dipped into the mercury, we can let it to be X. This is given as 2.50 centimeter, or we can say this is 2.50 multiplied by 10 raised power minus 2 meter. In the same region, there is a magnetic field perpendicular to this plane of paper and directed into it. And the value of this magnetic field has been given as 0.00650 Tesla. Now, it is said that as we switch on the current in this circuit, in the first part of the problem, the wire jumps up to a height of 35 centimeter beyond its initial position. So, first of all, this wire will move up to a height of 2.5 centimeter into the mercury. Then the height raised in air is height raised in air under the influence of gravitational acceleration is h dash is equal to 35 minus 2.5 centimeter, or we can say this is 32.5 centimeter. So we have to find the initial speed of the wire as it leaves the level of mercury. So to find it, we use the equation v square is equal to u square minus 2gh, where v is the final speed achieved by the wire at the highest point, and necessarily it is 0. As it is the highest point, the wire does not go beyond it. So it becomes 0. U, which we have to find the square of this u, minus 2, 9.8 meter per second square, multiplied by the h, which is 32.5 divided by 100 meter. So the expression for this u here comes out to be the square root of 2 multiplied by 9.8 multiplied by 32.5 divided by 100. Hence, it comes out to be square root of 6.37 meter per second, or we can say this is 2.52 meter per second, and it becomes the answer for the first part of the problem. Now, in the second part of the problem, we have to find the current passing through the wire when we switch on the circuit. So, first of all, to find it, we consider the motion of wire within the mercury. Considering the motion of vertical segments of wire within mercury, and for it, as the wire starts moving from rest, so we can consider u means initial speed is 0, final speed will be that which was initial speed for the first part, means u means that was 2.52 meter per second, and the distance traveled within the mercury is 2.5 centimeter, or we can say this is 2.5 into 10 to the power minus 2 meter per second. So applying the third equation of motion in kinematics, again here v square is equal to u square plus 2as. We get to know for v, the final speed, we know this is 2.52 to the whole square is equal to, for initial speed, 0 plus 2 multiplied by a, which we have to find. Actually, we have to find the acceleration of the wire when it is going up within the mercury, 2a into s, the distance traveled within the mercury, which is 100, 2.5 by 100 meter. So, solving this, we get an expression for the acceleration as this is the square of 2.52 comes out to be 6.37, then divided by 2 into 2.5 divided by 100, and finally it comes out to be 127.4 meter per second square. So now when the wire comes in the air, so taking the free body diagram of the wire in the air, the force acting upward is BIL, the magnetic force. The weight of the wire is mg, and as the wire is moving up, so an acceleration in it will be in upward direction, and that will be a. So the motion of the wire is still in the air, in the mercury, not in the air. So using this equation of free body diagram, the force in upward direction BIL minus mg is equal to, using Newton's second law of motion, this is ma, the net force equals to ma. So BIL comes out to be m into g plus a, or finally the expression for current passing through the conductor will come out to be m times of g plus a divided by v into L, plugging in all the values here. For the mass, this is 5.40 into 10 to the power minus 5. For G, this is 9.8 meter per second square. For A, we just found 127.4 meter per second square, and divided by the value of this magnetic field, which is 0.00650 Tesla, multiplied by the length portion of this length, horizontal length, which is 15 centimeter, or 15 by 100 meter. So finally, the answer for this current here comes out to be 7.6 ampere, and it becomes the answer for the second part of the problem. Now, finally, in the third part of the problem, we have to find the resistance of the wire, in ignoring the resistances of all other parts. So for I, this is 7.6 ampere, and it comes out to be 0.197 ohm. The answer for the third part of the problem.